Okay, so I'll pull up the same worksheet. And again, we're going to do the empirical formula problem first, and then we'll do the molecular problem at the end. There's only 2 problems. Once we get done, I'll count this as good and get you some easy points in the grade book. But what we start out here is this. We have, what's it say? A colorless liquid was found to contain 3.912% carbon, 8.76% hydrogen, and 52.12% oxygen. We ultimately want to determine the empirical formula. Now, empirical, if you're keeping up with the definitions, is that simplest whole number ratio. But again, what I'll show you here, we'll walk through the steps. And then to caveat on all of that too, I realized section 4 homework was probably pretty tough. So I told the other class, I'm going to tell you, if you go back and redo it, there's some problems you just couldn't get, and you want a better score, just redo it by the end of the week. That's fine by me, and get that accomplished here. And if I have some difficulties here. Good thing this wasn't a graduation requirement. Opening a box. All right, here we go. So, with these problems, it's very, very step by step, and we have to follow each of these steps. And I'll admit that there are some weird steps. So I'm going to start, and I would suggest starting on the very left side of your paper to make room for everything we're going to do. But the first thing that we need to do is just copy down the percents that we see on this particular problem. So we're going to start out here, and I'm just going to copy down 39.12% carbon, leave a little space, and then I'm going to put the percent for hydrogen, 8.76% hydrogen, leave a little space again, and then put down 52.12% oxygen. Now, this next step, it's real simple, but it's sometimes easy to forget. You take the percent and you knock it off and you make it to grams. Yeah, Ryan.
Do you have any darker markers?
Yes.
I'm sorry. I clearly not read what you're writing.
Let me try the standard black marker. Say yay or nay on this.
Got it.
Yeah, all right. All right, so the next easy step here. All we're doing is replacing percent with grams. So we have 39.12 grams of carbon. We have 8.76 grams of hydrogen, and we have 52.12 grams of oxygens. Questions up to this point? All right, so the next phase is we got to go grams to moles of each individual substance. So we'll stop and we'll pause and we'll make sure we have the number of moles for each of these substances. And we start out here with that conversion factor. Whenever we convert something, we got to have diagonal units cancel out. So because we have grams of carbon up here, what goes on bottom in terms of units? Perfect. Grams of carbon. I told you, hey, we're trying to get to moles of each of these elements. And now we get to this. To find out what number to put in this particular spot, we turn to the periodic table. So we look for that decimal number, that average atomic mass associated with carbon. And we round, for this case, 2 decimals.
12.01.
Perfect. Now, before I put down what Skylar told me, 12.01 grams per mole, I do this. That 12.01 is associated with what? Grams or moles? we can put down 39.12 divided by 12.01. Oh, that will work. And we can round to 3 total digits. And that's going to kind of be our standard from here on out, is 3 total digits is good to go. Anybody have it? Okay. 3.257.
Yes.
I'm going to round that to 3.26, and that would be moles of carbon. Now, we're going to go through and we're going to do the same thing for hydrogen, but it's a different element. So that means the molar mass is going to be different. Again, I'm going to ask you what unit needs to cancel out on the bottom. Perfect. Grams of H. I told you when we want to go to moles of H, we look for that molar mass, or we find it on the average atomic mass. Now I'm weird and I want 3 digits on, or 3 decimals for hydrogen's molar mass. It's the only one I want. 3 decimals, and if you round to 3 decimals, you get what value? 1.001. This one, right?
Yeah.
Okay.
No.
Perfect. So we take 8.76 divided by 1.008.
Yeah, sorry, 8.
Oh, okay, gotcha. Good to go. And what do we get for the number of moles of H here?
8.669.
Perfect. 8.69 moles of H. We got to do this one more time for oxygen. Again, we set up the conversion. What unit has to be on the bottom part of this conversion factor? Grams of O. I said, hey, let's go to moles of O, so that's going to be on top. And then what is the atomic mass or the molar mass for oxygen? 16. We put that big number on bottom, so 16 goes on top. And we have 1 mole on the portion, or the next to moles. 52.12 divided by 16. 3.26. Sweet. All right, 3.26. Now, I told you at the start there are some awkward steps with empirical molecular formulas. I consider this next step to be pretty awkward. What I want you to do is this. Everything to the left of these numbers that we just found, just blank out for a second, and ask yourself, of these 3 numbers, which one is the smallest? 3.26. So here's the really weird step. You take the smallest number of moles and you divide every number by that smallest number of moles. So the top number of moles gets divided by 3.26. That 8.69 is going to get divided by 3.26, and that oxygen gets divided by 3.26 as well. So anything divided by itself is always what? 1. So we get 1 mole of carbon. Someone help me out here. 8.69 divided by 3.26. 2.66. Okay, and 3.26 divided by itself again. Okay, so at this point in time, we now have more numbers to the right. If these numbers, right now are whole numbers, or very, very, very close to whole numbers, we can stop and be done and write the empirical formula. Are all of these numbers either a whole number or very, very, very close to a whole number? I'm talking you got to be like a couple hundredths away from being a whole number. This 2.2 or 2.66 is holding us up. So there's no steps or there's no method to the madness, but what I like to do is just kind of guess and check. So in my calculator I put 2.66 and I'm going to have to multiply it by something, so I start out and I multiply this by 2. What do we get if we multiply it by 2? 5.32. Again, is that anywhere close to a whole number? No. So now we've done 2. Let's do 2.66 times 3 now. 7.98. Is that really, really close to a whole number?
Yes.
Okay, so it is. What would that round to?
8.
It rounds to 8. Okay, so again, Skylar told me, hey, that is 7.98. Again, you have to be really, really close. I'm talking like 0.96 or 0.04 and below to be rounded. So this is 8 moles of hydrogen. Now, just like in algebra, what you do to one thing, you have to do to the other. So, because we multiplied hydrogen by 3, we also have to multiply carbon by 3. So now we get 3 moles of carbon. And again, what you do to one thing, you have to do to the other. So we have to multiply that oxygen by 3. So we get 1 times 3, 3 moles of O. Now, take a breath. I'm almost out of breath. We block out everything to the left, and we ask ourselves, these final numbers, are they finally whole numbers? Sweet. So, what we can do is this. Our empirical formula becomes what we have written down. And the way we do this is we write in order, top to bottom. We start out and we write C for carbon. The subscript becomes how many moles? So what subscript do we need to write? 3, too easy. What's the next element? 8, hydrogen. How many hydrogens do we need? 8, so we write an 8 subscript for hydrogen. And then oxygen is our next element. How many O's do we need for oxygen?
3.
Perfect. So, a couple of things. The empirical formula is C3H8O3. And then notice here, this is in the simplest version. You cannot divide all of these numbers by something and get it smaller. It'd still be a whole number. So, again, C3H8O3 is the empirical formula. Any questions on this one? Okay, we're going to do a very similar type of problem on number 2 altogether, but we're going to go one step further. So I'm going to get that problem up, erase the board, and then we'll go from there. So let me pull that problem up. Perfect. And do some erasing. Okay, so this right here, it reads a little bit differently. So it says, hey, we have an analysis that comes out and we have 26.76% carbon, 2.21% hydrogen, and 71.17% oxygen. This compound, whatever it is, has a molar mass of 90.04 grams per mole. This stuff is new. We don't do anything until the end. Ultimately, we want to determine the molecular formula. So the molecular formula is some multiple of the empirical formula. First step we have to do is find that empirical formula. So again, we make life easy and we write down exactly what's given in our percent. So we have 26.76% carbon. Give some space here. We have 2.21% hydrogen. Give a little bit more space. And we have 71.17% oxygen. What do we do now? We take the percents and we make them what? Grams, right? So we get 26.76 grams of carbon. We get 2.21 grams of hydrogen, and we get 71.17% of oxygen. How about grams? Whoop, my bad. There we go. All right, what do we have to do in the next step here? Yep, we gotta convert grams to moles, so we set up that conversion. What unit has to cancel out on bottom? Grams of carbon to moles of carbon. Now this should be easy because we already have these values. So what value should be associated with grams from up above? Perfect, 12.01 grams per 1 mole. Someone help me out and calculate 26.76 divided by 12.01.
2.23.
Okay, perfect. 2.23 moles of carbon. We go down to hydrogen. Again, hydrogen I'm weird about. We cancel out diagonal grams of hydrogen. On top we go to moles of hydrogen. What number gets associated with grams of hydrogen?
8, sorry.
There we go, 1.008 for every 1 mole on top. Somebody help me out, 2.21 divided by 1.008.
2.19.
Perfect. So 2.19 moles of H. And then we have to do this for oxygen. So again, you've told me before, grams has to cancel in this case. Moles is on top. What number in this case is associated with grams?
16.
Perfect. 16 flat or 16.00 per 1 mole. Someone help me out on this one.
4.45.
Perfect. 4.45 moles of O. So again, I always consider this next step to be awkward. What I do is I blank out everything that I've already done. I've done a lot of work so far, and I just look at my numbers to the right. I ask myself, which of these numbers is the smallest number? 2.19. What do we need to do with the 2.19? Divide every single number here. So 2.19 is going to get divided by 2.19. 2.23 is going to get divided by 2.19. And 4.45 is also going to be divided by 2.19. Now remember our rules. When we do this division right here, If we're close, so like 0.96 or 0.04, we can round to that whole number, or we get a whole number. That makes life real nice and easy. So we'll start here. 2.19 divided by itself is too easy. 1 mole H. Then 2.23 divided by 2.19. 1.02. Again, is it in that range so we can round to a whole number? Sweet. We gotta be close. We can't just be willy-nilly. We gotta be close to that whole number. So again, my rule of thumb is 0.96 to 0.04. I can round to a whole number in this particular step. 4.45 divided by 2.19. 2.03. We're getting close there, but can we round? Perfect. So this becomes 2 moles of O. Now, again, once we have these numbers divided, we ask ourselves one more time to make life easy, are these numbers a whole number? Yeah, sweet. So that saves us a step. We don't have to worry about that multiplication business, because right now, after we've done this step, they're a whole number. So we only do the multiplication business if we need to get one of these numbers to a whole number. Not happen on this one because it makes life easy. So what we can do is write down the empirical formula. So we ask ourselves, where we start with the first element, which is C for carbon. We have C. How many C's do we need in our formula? 1. Sweet. Don't have to put anything. H for hydrogen is our next element. How many H's do we need? 1. Making life easy. The final thing is O. How many O's do we need? 2. Too easy. So the last problem, we would have stopped and been done because that's our empirical formula. But now we have to go and we have to worry about this molar mass business. So what we need to do first, we'll get to using this here in a second. We have our empirical formula and we need to find the molar mass of this entire formula. So what we do, or what we have been doing, is we list out each of the elements and we put the molar mass. Now this should be easy because we had to use it earlier. So what is the molar mass for carbon? Yeah, 12.01 grams per mole. We look to our formula. How many carbons do we have to multiply that number by? 1. So we multiply this by 1. That makes life real easy because it stays at 12.01. Hydrogen, what's the molar mass there? Yep, 1.008 grams per mole. How many H's do we have in our empirical formula? We have 1. Again, that makes it real nice because we have just 1.008 grams per mole. And then oxygen, what is the molar mass for oxygen? 16 flat, or 16.00 grams per mole. Now, what do we need to multiply oxygen by? 2, because we have a 2 in our formula. 16 times 2 becomes what? 32. We have all these numbers on the right hand side now. What do we do to get our molar mass of our compound? Add them all together. And you, when you do this, you can just round to 2 decimals. 0.2, Regan? Okay, so again, we have 45.02 when we add these numbers up and divide by 2. Now comes kind of this third awkward step, and that is the ratio. So the ratio is going to be this. You put the given molar mass. Again, this will be given in a problem. It's going to say, hey, this compound has this particular mass or molar mass. You put that on top. So we have 90.
Pardon the interruption, please, but if I could have everyone's attention just for a couple of minutes. Students, first of all, I'd like to say thank you for following the arrows in the hallway. I've been out and about, and you guys are doing awesome. I really, really appreciate that. Please keep up that. When we start lunch in just a few minutes, what you will do is report to your lunch zone. I sent an email out the end of last week or the beginning of this week. You should have received it. If you have not looked at that, you need to, but you are assigned to a specific lunch zone. You are either assigned to the cafeteria, to the library, to the hallway near the cafeteria, or the gym. So please look at that if you have not done so, and that is where you report before you ever go to the lunchroom. Students who are eating in the lunchroom will be first in line. I will come to the other lunch zones and dismiss you when it is time for you to go get in line. Thank you. We'll get through this and we'll get better at it each day. Again, thank you for your cooperation.
All right, so ratio. Given molar mass, then you divide it by the molar mass that we just spent the time calculating. So we're going to take 90.04 and we're going to divide it by 45.02 grams per mole. Exactly what? 2. If this is just over a whole number, round it up or down. It will be very, very close if it's not spot on like it is on this one. Now this ratio, we got to do one thing with this, one final step to get our molecular formula. That tells us what we need to multiply each of these subscripts from the empirical formula to get to our molecular formula. So what I do is I put the empirical formula in parentheses, and then I say, hey, times 2. So now, carbon times 2 means we have how many carbons? Yep, so our first part here is C2. H times 2 means we have how many H's? H2. And then our O2 times 2 becomes what? 4. So C2H2O4, this becomes our molecular formula. And does everybody see that in a molecular formula, those subscripts can be divided and simplified? You can get it smaller and smaller. That's the whole point of molecular formula. I will say sometimes, there's very rare circumstances, the empirical and molecular match up, but most of the time they're going to be a multiple of that simplified form. All right, I'm just going to come by and check, see if you did it, get you some easy points. And then tomorrow there'll be a 2-question quiz. One you're doing empirical, one you're doing molecular. That's all we're doing tomorrow.